The questions from yesterday's lecture. Okay, so let me begin. So yesterday we calculated the partition function of the harmonic oscillator. So today we are going to first calculate some correlation function for the harmonic oscillator, and then we move on to field theory. So the correlation function that will be calculated are the imaginary time correlation function. Later on we will see its relation with the real time correlation functions. So we define this operator q hat of tau as e to the tau h hat e to the minus tau h hat. Okay, hat denotes that it's an operator. And then we define the two-point function g of tau as trace e to the minus beta h hat q hat of tau q hat of tau. So this I can expand out, trace e to the minus beta h hat e to the tau h hat q hat of 0. Which is trace so one can easily find its path integral representation. So basically we divide this again into these products e to the epsilon h hat, e to the epsilon h hat, and so on. And then in appropriate position we insert q hat. Okay, and then write down the path integral representation. Okay, this is the standard way one gives path integral representation of the correlation functions. So instead of going through derivation, let me write down what the expression is. So g of tau will be given by integral dq e to the minus the Euclidean action q tau q0 and I'll take tau to be between 0 and beta. Okay, so this is already time ordered. Okay, because tau is larger than 0.
Denominator trace of e to the power minus beta.
Yes, you are right. So this has to be divided 1 over trace minus beta hat. Okay, so 1 over z basically. Okay, and that's what is appearing here. Okay, now let me remind you the expression for SE. So this was given by m integral 0 to beta d tau of dq d tau squared plus omega square q square but we also rewrote this in terms of components. So m t First we wrote it as minus equal to infinity by 2 I'll remind of what the Q lines were. So Q we had expanded because Q is periodic. Q of tau we had expanded the sum over there is a factor T in front is equal to minus infinity to infinity Q tilde n I omega n tau omega n was 2 pi n by beta. And then this we had rewritten as okay, so going from here to here, we had to use appropriate reality condition on the Q tilde n to write this in terms of these coefficients ans and bns. Now, before we proceed, let me just point out that this action that we have written, one can think of as the action of a 0 plus 1 dimensional scalar field. Right? Because Q, if you think of as a 0 plus 1 dimensional scalar field, then this is like the kinetic term, this is the mass term. Okay, there is a half here. Okay, this is like the kinetic term, this is the mass term. And this is an overall multiplicative factor that appears in front of the action. Okay, we will leave it as it is. Without this, this is just the action for a 0 plus 1 dimensional quantum field. Okay, I am pointing this out because we will see that the Green's functions that we get in principle could have been read out just from this action and our usual knowledge of quantum field. Okay, but let's calculate the Green's function anyway. Okay, so now the task is straightforward, right? We substitute this form for Q, okay, in Q of tau, Q of 0. Reinterpret this dq as the integrals over the ans and the bns, okay, and then carry out the integral. So to do this integral, okay, we have to basically use this fact that an, to take an am e to the minus ac dq over integral e to the minus ac dq. The only relevant integral is that, first of all, you can see that because I didn't write the action in terms of ans and bns. Let me do that here. So I'll do that. So let me write AC in terms of ans and bns. AC is, so Q in terms of Qn it's given here. In terms of ans and bns, it's MP Okay. So the action is quadratic in ANs and BNs without any cross term. So this basically shows that this an integral of this kind must be proportional to delta mn, right? Because if you have two different a's, okay, then just by a goes to minus a symmetry, that integral will vanish. Okay, so this is proportional to delta mn. So this is delta mn, and then I can write integral dan an square to the power minus mt omega square plus omega n square divided by integral dan to the minus mt omega square plus omega n square. Okay, so this is an elementary integral. Is this clear? All the other factors will cancel, right? Between numerator and denominator. Only the an integral in this dq will survive. And this gives you delta mn over 2 mt omega square plus omega n square. Okay, you can get it by differentiating with respect to this parameter m. Okay, this is an elementary integral. Is this okay? So now, what is the task? We basically have to express q tau q0. Okay, you can write a similar integral for a0, okay? And the bn. I mean, bn will be exactly the same, right? Because it appears exactly in the same way. Okay? And if we have a0 square, okay, then the only difference is that instead of 1 over mt, you will get 1 over mt by 2, right? Because the coefficient of a0 square has a half in it. So for a0 square, this factor of 2 will not be there. Right? That's the only difference. Okay, otherwise it just follows. Okay, so now I can erase this because q tau is there. So we have q tau q0. This is the one object whose expectation value we are calculating, right? So we just substitute from here. Q tau is given by this and q0 is the same thing with tau equal to 0. Then you get a quadratic term, okay, which involves n from here and then m from there. Okay. But of course only the m equal to n terms will contribute, right, because of this delta n. So q tau q0, this product, okay, let me write down the relevant terms that are going to contribute. So that is a t square sum over n. So let's look at the coefficient of n. It's e to the I omega n tau plus e to the minus I omega n tau. Okay. So e to the I omega n tau plus e to the minus I omega n tau. And then there is a coefficient of for q0, right? It's just the same thing with tau equal to 0. Okay, so that's 2 an square. Is clear? So in the q tau q0, this is the relevant term that is going to contribute. For b, you would have gotten ibn, okay, times e to the I omega n tau minus e to the minus I omega n tau. But then when you take the q0 part, right, at tau equal to 0, these two terms exactly cancel. Right? So q0 doesn't have any b dependence. Right? In q0, these two, this is just ibn minus ibn, so they just cancel. So there is no quadratic term in b. Right? You can get a b from q tau, but not from q0. The only other term T square A0 square. So these are the terms which are going to contribute. And now I am going to use this to evaluate this. So the expectation value, so G of tau will be given by T square sum over n, 2 e to the I omega n tau plus e to the minus I omega n tau times 1 over 2 mt 1 over 2 mt omega square plus omega n square plus T square. For A0 square, you just don't have this 2, right, as you described, because of this mt over 2 that is coming here. So 1 over mt. This is n equal to 1 to infinity. Okay, because these sums are from 1 to 2. Is this okay?
Do you have to divide by z or is that?
Yeah, in the definition of G of tau, right, yeah, you have to divide by z, but what I have written here is that ratio already.
Oh,
This is coming from, when you divide by z, all the other integrals cancel, and this is what is in the denominator, right? So here the division of z by z is automatic. Is this clear? Right? Because this is already the ratio, right, of the.
Q tau Q0 multiplication.
Yes.
There will be no term A0 and N.
Yes, A0 n is there, but when you integrate, that gives you 0, right? Because the exponential has A0 square and an square, but no cross term, right? So the A0, suppose you have A0 n, right? Then the A0 integral will vanish by A0 goes to minus A0 symmetry. Yeah, that's why you only pick up the diagonal terms, right? Even the an, am terms go away because of this. Okay, so now we can just write it in a somewhat neater form. So I will now rewrite G of tau. For t, and one factor of t goes away, both. Is this okay what you are doing? This 2 and 2 cancels, right? So t over m. Okay. Here you have a I omega and tau plus e to the minus I omega and tau. Okay. So using that I can extend this from minus infinity to infinity without the 0 term, n equal to 0 term. Okay. N equal to 0 term, this is coming from here. Okay, so this is the full answer for the Green's function. Now let's compare this with what we would have gotten if you are doing zero temperature field theory. Okay, suppose you are doing zero temperature Euclidean field theory. Okay. What we would have gotten, so this is 0 plus 1 dimensional field theory. Right? What we would have gotten, so zero temperature field theory we would have gotten integral e to the I e tau over e square plus omega square d by 2. So let me explain this. So this is omega is like a mass. We saw that when you compare the harmonic oscillator expression, right? When you think of this as 0 plus 1 dimensional quantum field theory, right? Omega is like a mass term, right? Because half m omega square q square is the term that is appearing in the action. So this is like p square plus m square, right? Okay, there is only one component of p, that is that you are calling e. Then you have the usual integral d over 2 pi and the Fourier transform. This 1 over m over here is a reflection of the fact that the Euclidean action that we wrote down had an overall factor of m multiplying it. Right? So if there is an overall factor of m multiplying it, the propagator will have a 1 over m. Right? That's this 1 over m. So this would have been the zero temperature field theory answer. Now the relation between this and this is simply that this, if you discretize, you get here. Okay. So what is the discretization? Discretization that you take e to be 2 pi n over beta. You allow, instead of integrating from n equal to minus n to infinity, you sum over n from minus n to infinity. And you think of this 2 pi over beta as a lattice spacing. Right? 2 pi over beta, beta is very large in the zero temperature limit. Right? So this is like the lattice spacing. So integral d will go over to sum over n 2 pi over beta. Is this clear? This is the way one discretizes a continuous integral, right? That instead of integrating, you just discretize and you multiply, you sum over the lattice points and you multiply by the spacing, which in this case is 2 pi by beta. So in that case, this integral, so 1 over m integral e to the I e tau over e square plus omega square d over 2 pi will go over to 1 over n sum over n e to the power I tau 2 pi n by beta, and here 2 pi n by beta square plus omega square. Then you have 2 pi over beta, that is 2 pi over beta factor here, and then 1 over 2 pi because you had a d over 2 pi. So this to cancel, 1 over beta becomes t, so it becomes t over m, and sum over n e to the I omega n tau, this is exactly omega n, 2 pi n by beta over omega n square plus omega square, and that's exactly this. So the upshot of this is that if we had done, treated this as an Euclidean quantum field theory, 0 plus 1 dimensional Euclidean quantum field theory, taken its propagator and simply discretize it, okay, instead of the energy integral, you discretize it over the these much number of frequencies, you would have gotten the correct propagator. So I am emphasizing this because when you do Euclidean quantum field theory, okay, you are not going to derive the propagator every time. Okay. We'll use a known form of the propagator that we know from standard quantum field theory result, and simply discretize. Instead of energy integral, we will do the sum over mass over frequency, and that's what will give the correct propagator in the finite quantum field theory. Is this point clear?
This discretization you would set beta infinity.
Yeah, in the beta goes to infinity limit, the discretization actually goes to the continuum integral. Right? So that gives a zero temperature field theory. But if you want to do it for finite temperature, right, you will not set beta equal to infinity. Right? So the idea is that if you take the zero temperature field theory propagator, right, write it in an integral of this form, and just discretize it over a lattice of spacing 2 pi by beta, that gives the propagator in the finite temperature quantum field theory. Yes, that's the way we will find the propagators in finite temperature quantum field theory, instead of having to go through this analysis again and again. Of course, one will get the same answer. Right? I mean, if you start with the finite temperature quantum field theory path integral and just follow this procedure, you will get the correct answer. Right? But the simplest way to get to the correct answer is by recognizing that all it involves in going from a zero temperature field theory to finite temperature field theory is discretizing integration over the energies.
Is there a general reason for that? I mean, this.
I think the general reason is simply that when you look at the Euclidean action, right, the only way it differs between finite temperature and zero temperature is the fact that you make the fields periodic. Right? So in the energy space, right, it's basically continuous energy variable you are just making into a lattice. Right? Otherwise the manipulations are all identical. Right? There you do Fourier expansion and then in energy and carry out the in time and carry out the analysis. Here the Fourier expansion will involve discrete Fourier expansion. Right? Otherwise it is an identical manipulation.
So is that condition it's like analogous that where we put those in like time zero temperature QFT, the fields vanish off at infinity. So is it analogous like?
Yeah, or you can think of it as a periodic. You put I mean the way you can do zero temperature field theory is that you assume that there is a periodic boundary condition, right? And then at the end you take the period to infinity. Right? Here, all you are doing is that you are not taking the period to infinity.
What if you consider high temperature and this lattice spacing is not?
Yeah. So the point is, once you have gotten the discretization, right? This formula, of course, is valid for all temperature. Right? So what I am saying is that in order to get to this formula, right, you can take the formula in zero temperature field theory and simply replace all energy integrals by discrete sum. Right? Then that formula you can use for finite temperature, high temperature, anything that you want to do. Right? That's an exact formula. Right? All I am saying, to get to that exact formula, you can start with the zero temperature result and discretize the energy into an energy sum. Right? You can derive it from first principle every time. Okay, but once you understand the physics, we don't have to do it from first principle, right? We already know how to analyze the normal quantum field theory at zero temperature. Right? And all you have to do is that you replace the energy integrals by sum over discrete modes. And this is just an illustration. Here we did derive it from first principle. Okay, but what we see is that we could have, once you have gotten this answer, we recognize that we could have gotten it just by taking the usual energy integral and discretizing it. Right? Because this is what we would have calculated as the propagator of a 0 plus 1 dimensional quantum field theory.
I don't know. Suppose if there are interaction, then whether this procedure I can take, if I know, suppose by some method I know the propagator for some interaction. Okay.
Yeah. So the point is, so when you do perturbation theory, right, then everything is ultimately expressed in terms of free field correlation functions. Right? You take the interaction vertices, right, and you, take the product of interaction vertices, but ultimately everything is free field correlation function. Right? So once you have expressed things in terms of free field correlation function, you follow exactly the same procedure. Right? In the Feynman rules, you just replace the energy integrals by energy sums. But this is only in perturbation theory. Right? If you try to take into account interactions non-perturbative, then of course you have to devise new methods.
But up to there it is valid. One can do.
Yeah, if you do perturbation theory, then this procedure works perfectly fine.
But what about adiabatic switching of interaction? Suppose I was doing a interacting zero temperature field theory, then I thought one has to work with states or which are far at minus infinity and infinity.
Oh, that is for the S matrix. But for Green's functions, right, you can calculate the Green's function by standard perturbation theory. Right? So the Green's function. So formally, all I am saying is that formally the procedure is exactly the same. You write a path integral, right? So how does the path integral of a zero temperature field theory differ from the path integral of a finite temperature field theory? It's by imposing the periodicity condition in time. Right? In Fourier space, it means that you have a discrete Fourier transform instead of a continuous energy integral. After that, you carry out identical manipulations. I mean, in fact, you don't even have to take this rule. I mean, you can start with the path integral again and carry out the analysis. Right? All I am saying is that instead of doing all that work, right, once you know how it works in zero temperature field theory, right, you can directly figure out what the answer will be in a finite temperature field theory by replacing the energy integrals by sum over discrete forms. Right? It is just manipulation of the path integral. So this, whatever I am saying here, is at a level of manipulating the path integral. Okay, is this okay? The other questions? Okay, so now let's evaluate it. Okay, so this sum we have to calculate. And we do it by following the same trick that we did yesterday. Yesterday, if you remember, we evaluated the sum like this, but with 1 over omega square plus omega n square. Right? This was in the context of calculating partition function. The derivative of the partition function had a sum of the form 1 over omega square plus omega n square. Here we have e to the I omega n tau, but the procedure will be the same. So we write g of tau as a contour integral. Let me t over the outside. A contour integral dy. Now you have to introduce something which has poles exactly at omega n. So I write e to the power I beta y minus 1, and in order that the residue is 1, I put I beta. You see that this has poles exactly at y equal to 2 pi n by beta. Okay, those are exactly the omega n's. And then we write e to the I tau y over y square plus omega square. This is clear? And the contour, this is the y plane. Contour is basically anti-clockwise contour like this. It goes from minus infinity to infinity below the real axis, then comes back from plus infinity to minus infinity above the real axis. Okay, so it picks up all the poles that are on the real axis, which are the zeros of this. Okay. And now the idea is that we deform the contours. Okay, so there are two other poles at I omega and minus I omega. Okay. So this contour, okay, the contour on top will deform to plus infinity. Contour below will deform to minus infinity. And in that process, we pick up the poles, contribution from the poles at I omega and minus I omega. Okay, but you have to make sure that when you deform it to I infinity or minus I infinity, the integrand goes to 0, because you don't want any contribution from plus minus I infinity. Okay. So that's not hard to check. So let's check what happens when y goes to I infinity. When y goes to I infinity, this part of course goes to 0. It's not worrisome. This one goes to e to the, suppose y equal to I1. Let's call it y equal to IU. Okay, and u is going to infinity. Then this becomes e to the power minus tau u. And e to the I beta y, this becomes e to the minus beta u, right? E to the minus beta u is going to 0 as u goes to infinity, so it's minus 1. So this is going to 0 as u goes to infinity. Okay, so y equal to I infinity is not a problem. If y we write as minus iu, okay, and then take u to infinity, that's like y goes to minus I infinity. Now this goes as e to the power tau u. Okay, so it's growing as u goes to infinity. But now you see the denominator, now this is going to e to the beta u, right? So e to the beta u, and then minus 1 you can ignore because this is a dominant contribution. This ratio still goes to 0 as long as tau is less than beta. So this goes to 0 as u goes to infinity if tau is less than beta. Okay, and this of course requires tau is greater than 0. Okay, and that's of course the range that we are working in. Right? Tau lies between 0 and beta. So as long as tau lies between 0 and beta, there is no problem in deforming the contour all the way to infinity. Right? Because in one case it vanishes because this factor itself vanishes. In the other case it vanishes because this factor grows but this factor grows faster.
So why not you are considering the factor y square plus omega square when y?
Well, the point is the exponentials are always dominant. If there is a large exponential, right?
Right. But in that case, there is actually 1 by y square is there.
Mm-hmm.
Right. So that is 1 by u square kind of thing.
Yeah, but e to the u over u square will not help. See, u square is irrelevant as long as there is an e to the u, right?
Okay, yeah.
So yeah, y square is useful. Okay, on the real axis, for example, you can say that this controls the divergence, right? But towards the imaginary direction, right, this y square is not of very much use because these are the dominant contributions. Right? That's why I looked at these factors.
You need to
switch from logical,
Pardon?
using logical.
Yeah, one can show from the orbital root, but the point is, so these are the dominant object quantities that will contribute at plus minus I infinity, right? Because exponential is always growing faster than u square. I mean, quadratic, right? For example, if this factor was not there, right, then the fact that this is 1 over y square wouldn't have helped, right? As tau goes to minus I infinity, it should just blow up.
Sir,
Yes.
the interpretation of this series sum versus this integral that you were talking about,
Yes.
I think the whole issue is it that in the finite limit, basically when you cannot attain to the true differential limit when you are having a finite temperature effect, so the series sum cannot be interpreted as an integral.
No. So this is a separate thing. Okay. This was yes. So this is of course not the same as this. Okay. So this integral, this is not identical to this. So I was saying this because in the zero temperature limit, this is the correct answer, and the discretization of this gives to this sum. Okay. That's just something that you note here because you are going to make use of this later. This is completely independent. This is an identity. Okay. Then I just rewrite this as this. Because when you carry out the y integral, right, you pick the residues from these poles. Right, because there are poles over here. Okay, this contour is going to be given by sum over residues from these poles, and that's exactly this sum. Right? So the equality of this and this is an identity. Right? This is different. This is something that I said that you can guess what this form would be by starting with a zero temperature Green's function and then discretizing the energy. Okay, so I think one shouldn't confuse between what I did here and what I am doing here. This is an exact evaluation. This is an exact representation of that sum. Is this okay?
But I mean, this probably holds, but you need to show well that in arbitrary directions it goes. I mean, just not purely in the complex because you are deforming.
Yeah, you can have a part, a real part also.
Yes, and it will.
As long as the imaginary part is going to infinity.
Yes.
Right?
So
This is going to see.
so yeah. So arbitrary direction. So
Yeah, and if it goes on the real axis, then this 1 over y square is going to do the job. If these are not growing, right, along the real axis, these are oscillatory, then 1 over y square is good enough to make it converge. Is this okay? So this represents, so this integral, so this is of course, okay, the fact that that is equal to this didn't require any of this, okay, it's an identity, but the fact that you can now deform this contour to infinity, picking up the residues from plus minus I omega, okay, that requires the fact that this factor falls off at plus minus I. Okay, otherwise you couldn't have defined the conflict. So this basically gives G of tau. There is a minus sign, because now when you deform it, it's going to enclose these in the clockwise direction. So minus sign, T over M, and then I beta over e to the power I beta y minus 1, e to the power I tau y over y square plus omega square at y, and then there is a not y square, it's omega square. The residue is 2y, and you have to sum over y equal to I omega plus y equal to minus I. Okay. So this expression you have to evaluate at y equal to I omega, at y equal to minus I omega, and add them up. These are the sum of the residues. So this, let me write one more step, minus T over M I beta over I beta, then we'll get 1 over, this is the I omega residue, minus e to the minus beta omega minus 1 times e to the power minus tau omega by twice I omega plus 1 over beta omega minus 1 e to the power tau omega is clear. These are the sum of the two residues, and now I'll go to write down the final answer. So this is 1 over 2m omega, okay, t cancels with this beta, times cos hyperbolic omega beta by 2 minus tau divided by sin hyperbolic omega beta by 2. Okay, this is the form of the 2-point Green's function that we calculated in the Euclidean conflict theory. Is this okay? Okay, now the point is that this, of course, could be calculated in a much simpler way by directly using the operator formalism. Okay, so the reason that you are calculating this 2-point function is not because the path integral makes this calculation of 2-point function easier, okay, but we just want to make sure that path integral gives the right answer. Okay, because eventually you are going to generalize to quantum field theories where you need path integral representation. But let's just make sure that path integral has given the right answer. Okay, so we calculate it directly using the canonical formalism and see what we get. So operator formalism. So in the operator formalism, G of tau is 1 over z trace of e to the power minus beta minus tau h hat q hat e to the minus tau h hat q hat. right? So these are I now express in the energy eigenbasis, sum over n. N, okay, I will not write the sum over n, it should be understood. N e to the minus beta minus tau h hat q hat m e to the minus tau h hat q hat m. Okay, I introduce two complete set of states, n and m. Okay, this n is implementing the trace. Okay, you are summing over n, and this sum over m is this identity. Okay, that I insert in the middle. Okay, so these we are taking to be energy eigenbasis. So this then gives you, this is an eigenstate of h hat. So you get e to the minus beta minus tau n plus half omega. Okay, because this acts on n, producing this number over here. Similarly, we get e to the minus tau times m plus half h bar, m plus half omega. Okay, because this is an eigenstate of h hat again. So e to the power minus tau m plus half omega. And then we are left with n q hat m q hat n. Is this okay? Now we are going to use the fact that q is expressed in terms of the creation and annihilation operator. So let me write the correct formula. So q is square root of 1 over 2 m omega a plus a dagger. So this is the annihilation operator and this is the creation operator. Okay. So we insert a plus a dagger here. Okay, and similarly a plus a dagger here. So you get 1 over z Now you see here, once q has become a plus a dagger, m can either be n plus 1 or n minus 1, right? Because a raises a dagger raises the number by 1, a lowers the number by 1, right? So we get delta m, so I can write here delta, so there is a sum over m and n, let me write it. Over m and n. So delta n m plus 1, or let me write delta m n minus 1. So m is equal to n minus 1. In that case, the result is n let me put this 1 over 2 m omega outside. That's square of this will be 1 over 2 omega. Because there are two factors of q hat, there will be 1 over 2 m omega. Okay. So if m is n minus 1, Okay. Then this has to be a dagger. Is this clear? See, if m is n minus 1, then this has to be a dagger because a dagger has to raise this so that you get a non-zero inner product, right? And similarly, this has to be a because a has to lower this to get a non-zero. Then there is another term, delta m n plus 1. Then it will be n a n plus 1 n plus 1 a n. Sorry, a dagger. Is this clear? But now, you see this object, suppose I replace it by sum over p, pp. Only p equal to n plus 1 can contribute, right? Because any other p is going to give you 0. So this I can just replace by sum over p, pp, right? Which is identity. Okay, so this part I can just replace by identity. Similarly, this one, again I can replace it by sum over p, pp, and that's identity. So I can now rewrite this part, this square bracket part, the curly bracket part, I can write it as delta m n minus 1 n a dagger e n plus delta m n plus 1 n a dagger n.
Do that there itself.
I could do that there.
You inserted n.
Yes.
After you took out the
Yes, I could have done that, except that there was an a square and a dagger square which I have to ignore. Right? I would have to say that a square and a dagger square do not contribute. Because here there will be also a square and a dagger square, right? Yes, I could have done that there. So now a dagger is just n. Right? A dagger acting on n gives you n. A dagger gives you, I think, n plus 1. Right? If a dagger is a dagger a plus 1, then that gives you n plus 1. So now it's an elementary sum, right? We just set m equal to n minus 1. Okay, in this. So this m is not the same as that m. So let me make it capital M. Okay, this is a m parameter, right? Mass parameter. Okay. So now it's an elementary sum. Okay, I'll leave it as an exercise to check that this is the same as this. And then you check that after you perform the same, you reproduce what we have to write. Okay, so this basically shows that the Euclidean method or the path integral method does give the same correlation function as you would have gotten by standard canonical formulas. Okay, are there questions? Okay, so now we are going to move on to field theory. Okay, so I'll start with the simplest case, T-scalar field theory. So D, eventually you are interested in D equal to 3. Okay, if you want to do 3 plus 1 dimensional theory, okay. But I'll keep D in the intermediate stages because you will see that you have to do dimensional regularization. Okay, there will be various divergences. Okay, as is normal in quantum field theories. Okay, so I'll keep D unspecified till the end. Okay, at the end you will have to set D equal to 3 minus epsilon. So the Minkowski or the Lorentzian action is minus half integral d dx dt and then okay, so our notation for a metric is the time component is negative, okay, all the space components come with positive metric. So this is the form. So the Euclidean version of this is half integral d dx d tau, then you have del tau phi square plus that phi square plus m square phi square. So the strategy that we will be following is to try to map this into a collection of harmonic oscillators, okay, all at finite temperature, and then just calculate the partition function by adding up the partition functions or taking the product of the partition function of individual harmonic oscillators. Okay, so first you want to see that this becomes a collection of harmonic oscillators. Okay, so let's begin with a finite periodic box. Of length right? Okay, I equal to 1 to d. Then you can expand phi as 1 over beta times v sum over n sum over k phi tilde omega n k and then to the I omega n tau plus I k n dot x. So Kn basically means, or Ik, let me write k dot x. So k is discrete. So ki is given by 2 pi ni by li. Okay, eventually we will convert this to an integral. Okay, V is the volume. So V is L1, L2, L3. So this is just a normalization, okay, similar to what we had earlier. Earlier for harmonic oscillator we only had a 1 over beta or equivalently t. Now we have 1 over beta as well as L1, L2, L3 because all directions are periodic. And the reality condition is phi tilde star, phi tilde omega n a star is equal to phi tilde minus omega n minus.
L1 into up to L d minus 1.
Yes, LD, yeah, L1, L2 up to LD. Okay, so eventually, of course, the volume will go away. Now you can calculate this AC. Okay, I'll do this, but this is straightforward. and this becomes P over 2D sum over omega n and k omega n square plus k square plus m square okay, this is straightforward. You can substitute and evaluate. You just substitute this Fourier expansion and evaluate, and this is what you will find. So this we can compare with the harmonic oscillator action. Compare with harmonic oscillator action, which had the structure that AC is equal to m d by 2 sum over n omega n square plus omega square. But we have q tilde n, q tilde minus n, but this I can also write as m times t by 2 sum over n omega n square plus omega square q tilde n mod square. Okay, because this is complex conjugate of q tilde n. So now let's compare this with this. Okay, let me put this as capital M. Okay, just not to confuse with the M, which is the field theory mass. Okay, this is the harmonic oscillator mass. This is the harmonic oscillator mass. So if you compare this with this, we see that it's for every k there is a harmonic oscillator with mass given by 1 over v and omega given by square root of k square plus m square, okay, which I'll call Ek. So the partition function of this field theory we can simply think of as a partition function of a collection of harmonic oscillators. Okay, so the product of the partition function of harmonic oscillators for every k. Is this clear? Log of the partition function is just the sum of the logs of the individual harmonic oscillator partition function. So let me remind you that the formula for the harmonic oscillator partition function it had two expressions. One is this, the other one was what we got from the path integral. Log of ZHO So you can take the log of that and you can write another expression. So this in fact I can write as minus beta omega by 2 because it's this is just a rewriting of this. Okay. Because 2 sine hyperbolic beta omega by 2 is like e to the beta omega by 2 minus e to the minus beta omega by 2. Right? Then you exponentiate and this is what you get. The other representation is that this is, if we use that one, okay, that's like, let's see, 1 over beta, so log of t minus log of omega minus sum n equal to 1 to infinity log of omega square plus omega n square plus sum n equal to 1 to infinity log of omega n square So let's just write this in a little better. So this is log of t log of t minus, okay, let me write this as half sum n equal to minus infinity to infinity log of omega square plus omega n square. This includes these two, right? Because you see that n and minus n gives the same contribution. Okay, so I have put a half and make this sum from minus infinity to infinity. Right, that takes care of this except the n equal to 0 term, and the n equal to 0 term here is a minus log omega term. Okay. And then plus I can write this as half sum n not equal to 0 log omega n square. Okay, let's write it this way. So I am not going to use these two expressions, okay, this expression and this expression, okay, to write the partition function of a scalar field. Okay. Now I am also going to take continuum limit. So sum over k will become v times integral p cube k or d dk over 2 pi to the d. Is this familiar? Right? Sum over k becomes basically L1, L2 up to LD over 2 pi to the d and then integral d dk over d dk. Right? That's only I got to use. That's this. So then we get z equal to, let's use the first expression, minus v integral d dk over 2 pi to the d times beta by 2, omega has been replaced by ek, right? Harmonic oscillator to omega replaced by ek, so beta ek by 2 plus log of 1 minus e to the minus beta ek And if you use the second expression over here, so this is P integral ddk over 2 pi to dt log t. Pardon? The ln z. Thank you. Yeah, Ek, let me remind you again, Ek is the square root of k square plus n square. Is this okay? I just use the formula for harmonic oscillator and then summed over all k to get the full expression for log z. Okay, for z it will be it should have been the product over all k.
This is the thermodynamic.
This is the, yeah, I mean you are taking the v goes to infinite limit because otherwise you couldn't have replaced this by integral. Is this okay?
This is free particle. You want to incorporate this conservation of particle number.
No, we are not going to impose a conservation of particle number. Right? You can introduce a chemical potential in principle, right? But you have not done that because eventually, right? Unless there is a really a concept, once you have interacting particles, right? This is like a free scalar, right? Right now it's a free scalar, so you could have imposed a chemical potential, but once you include lambda phi for interaction, for example, the particle number is not conserved. That's why you have not imposed anything. Are there other questions? Okay, now it's more useful to work with free energy per unit volume. So let me write down their expression also, and then we'll analyze the various limits of that. So free energy per unit volume this by definition is minus T over V log Z. Okay, I divide by volume because I want to do per unit volume, and then minus T log Z is the free energy. So it's easy to write down the expressions for those. Right? So just multiply by minus T by V. So let me write it here. So it's given by T integral d dk over 2 pi to t. Okay, t actually cancels this beta. Okay, so let me write this. Forget about this t. Half ek minus t log. This is the first expression, and then the second one is minus so let's put the minus sign inside. So minus T of T plus half minus T by 2
And the past expression, what will be plus sign in front of t?
will have plus sign, let's see, right?
Minus
Multiply by minus T, yes, I think this will be plus sign. Yeah, plus sign. Okay, is this okay?
You have taken Boltzmann constant to be 1.
Yeah, yeah. Boltzmann constant is 1 and H bar is also 1. Okay. Now the fact that these two are equal follows from the corresponding resultant harmonic oscillator, right? We showed that two expressions for partition function that we get in harmonic oscillator are the same, right? This is what we got from the canonical formalism, and this is what we have gotten from the path integral formalism, and they turned out to be the same. Now we have to do some work to remove divergences. Okay, because you see here, let's look at the zero temperature limit. And let's analyze this term. Zero temperature means beta goes to infinity. Okay. So in the zero temperature limit, this basically becomes goes to 0. And then log of 1 is just 0. Okay. So in the zero temperature limit, basically this term goes away. So what you are left with is, for the free energy is this. So at T equal to 0, so this is divergent. At T equal to 3, this is divergent. But this shouldn't really bother us too much, because this is simply a reflection of the fact that the vacuum has non-zero energy, right, or non-zero energy density. Okay, if you have a collection of harmonic oscillators, okay, we know the vacuum has non-zero energy density. Okay, and typically what we do in quantum field theory is to just set it equal to 0. Okay. A formal way of doing it is by saying that is to say that we add explicitly a term in the Lagrangian, okay, a constant term in the Lagrangian, that just cancels this integral. Okay. Now, this is really not necessary, because in quantum field theory you only see differences in energies, right? So even if you didn't set it equal to 0, you could have lived with it. Okay, in gravity of course things are different, but in normal quantum field theory you don't have to worry about terms like this. Okay. But nevertheless, it will be useful for us to subtract this off, okay, and set it equal to 0, because when we calculate, for example, the high temperature limit, okay, we will try to carry out a high temperature expansion. Okay. There again you will get some constant, okay. Whereas an overall constant doesn't make a difference. Okay. The difference in the constant term between the high temperature and low temperature expansion does make a difference, right? Because that's a difference in two free energies, right? Free energy at 0 temperature versus free energy at high temperature. Okay. So just to make sure that we don't lose out some important information, okay, what we are going to do is to subtract from the free energy, from this expression, okay, a term which exactly cancels this. This is a temperature independent term, right? A constant term. Okay. We will define our free energy by subtracting this. But before you subtract, you have to regularize. So let me call this F0. Okay. So in dimensional regularization, we have a formula ddk over 2 pi to the d k square plus m square to the power minus a. This is given by m to the power d minus 2a over 4 pi to the power d by 2 and then gamma a minus d by 2 over gamma of a. Okay. So here we take d equal to 3 minus 2 epsilon. Okay, eventually we are interested in taking the epsilon goes to 0 limit. Okay. A in our case is minus half. So you get f naught is half times m to the power, let's say 3 minus 2 epsilon minus 2a, so plus 1 over 4 pi to the power d by 2, that's d by 2 minus epsilon gamma of minus half minus 3 half plus epsilon over gamma minus half. Is clear? Okay, so we basically have to expand this out, okay, and keep the order 1 over epsilon term and the constant piece, right? These are the pole, okay?
Sir,
Yes.
in the gamma, in the numerator there will be epsilon by 2.
So I have taken d equal to 3 minus 2 epsilon.
Okay,
Okay, that's why it's epsilon.
okay, yeah.
Is that yeah? Here also it's
Yes.
minus epsilon.
Right, right.
Yeah. Okay. So the way we manipulate this is that we write gamma of minus 2 plus epsilon. We can write this in terms of gamma of 1 plus epsilon. The gamma of 1 plus epsilon, you have gamma of x is equal to x minus 1 gamma x minus 1, right? That's the formula used. Okay. So gamma of 1 plus epsilon is epsilon gamma epsilon. Okay. Then minus 1 plus epsilon gamma minus 1 plus epsilon and minus 2 plus epsilon. Is this okay? Okay, gamma of minus 2 plus epsilon I can write this way. And then gamma 1 plus epsilon has an expansion. Gamma 1 plus epsilon is 1 minus gamma e times epsilon plus higher order terms, okay, which we will write here. This is the Euler constant, gamma e. Gamma minus half, you can write as gamma of half divided by minus half. Okay, because gamma of half is minus half gamma minus half. So gamma of half I think is root pi, right? Minus 2 root pi. Okay, there is one more subtle point that you have to see. Here you have m to the power 4 minus 2 epsilon. 4 minus 2 epsilon, right? We will insert a arbitrary normalization mass parameter mu. Okay, eventually final answers will not depend on mu. Okay, because you are just inserting it. I will write this is mu to the 2 epsilon, mu to the minus 2 epsilon, and then re-express this as m to the power 4 mu to the power 2 epsilon, and then mu to the power minus 2 epsilon, and then mu square over n square to the power epsilon, mu to the power minus 2 epsilon is basically going to just supply the dimension of the free energy, right? Because the dimension of the free energy depends on the dimension in which you are living in, right? This mu to the minus 2 epsilon is going to supply that. So mu square over m square to the epsilon, and this I now expand m to the power 4 mu to the power minus 2 epsilon 1 plus epsilon log mu square over m square plus all epsilon square. Okay. So using this, I will now write down the formula for F naught. Okay, this is the F naught here. So exercise check is that F naught is given by so basically these terms that we are getting is because of the cancellation between this epsilon term over here, which is 1 over epsilon that comes from the pole. So log mu square plus m square plus log of 4 pi minus gamma e plus 3 pi. So the point is that for zero temperature, in the zero temperature limit, if we want the free energy to be 0, okay, that we are doing by hand. We just remove the vacuum energy by subtraction. If we want the free energy to be 0 at zero temperature, we have to subtract this from the expression that we have written. But this means that when you do a high temperature expansion, okay, of that expression, okay, we have to still subtract the same constant from the high temperature expansion, right? Because while the constant at zero temperature is up to us to choose, once you have chosen that, the constant at high temperature expansion, that is physically relevant, right? That's giving the difference between two free energies. So this is what we have to keep in mind, okay? That when you carry out, that we subtract this so that the first term basically goes away in the zero temperature expansion, that integral ek over 2 just gives you 0. Okay, because it exactly cancels this term. But now, when you do high temperature expansion, you have to subtract precisely this term. So tomorrow we will carry out the both the low temperature and the high temperature expansion, and we will see the significance of this term. I'll stop.